Good afternoon, everyone. I'm Xiaodi Dai, a PhD student from Ugent University. I'm very delighted to be here and present our works. The topic of our presentation is the influence of the temperature and activator type on the structure buildup of alkali-activated slag flash mixtures. So first, let's see the content of the presentation. We actually did some experiment work, and we also will discuss the results in the presentation. Basically, our aim is to determine the effect of the temperature and the nature of the activator solution on the structure buildup of alkali-activated slag flash paste, as we mentioned before. So we are using source measurement, small amplitude oscillation test to monitor the pastes from fresh state to hardened state. As you will know, typically two measured parameters can be used to evaluate the viscous elastic of the AAC pastes. One is the storage modulus, which is related to the elastic behavior of the material, and it is proportional to the energy stored in each cycle of the excitation. Another one is the loss modulus, which is related to the viscous behavior of the material, and it is proportional to the lost and dissipated energy in each cycle. And the loss factor is the ratio between G double prime and G prime. To make it more understandable, I use a reality exam to explain the parameters. As you can see here, if you release a rubber ball from a certain height after striking the ground, the rubber ball will go back to another new position. The lost height can be seen as a G double prime. The new position of the ball can be seen as a G prime, which is the stored energy. So let's see, next we will see the materials we used in our study. We used two different precursors, the GGBFS and the fly ash. As you will know, the fly ash has very spherical shape, and when you see the particle size distribution, you will find that the fly ash is more finer compared to GGBFS. As for the storage condition, all the materials and the activator solution were stored at 20, 30, 40, and 60 for at least 2 days period to measurements. For the testing devices, we were using the rheometer to evaluate the rheological behavior of the AAC paste, and the isothermal calorimeter to investigate the heat evolution of the AAC paste. So here is the experiment plan and the mixture design of this study. We have 5 different solutions. There are sodium hydroxide and two different the combination of sodium hydroxide and sodium silicate activator solution, and the sodium sulfate. And the last one is sodium carbonate. They have same sodium oxide content at 5% and the same water to bond ratio of 0.37. For the combination of the sodium silicate and the sodium hydroxide, they have two different MS ratio of 0.4 and 1.2. And we are using the blended system of 15% of slag and 50% of the fly ash. These 5 activator solution and their precursor will test at the temperature of 20, 30, 40, and 60 degrees. So let's see the methods we use for how to evaluate the structure buildup of the AAC paste. Before we perform the time sweep test, we have to determine the linear viscoelastic domain. For this LVED, we can determine this region by the strength sweep test. As you can see from here, the strength sweep test were with strength amplitude from 0.001% to 10%, and a constant frequency of 1 Hz were conducted to find the critical strain of these AAC pastes. As you can see from this graph, 2 main regions as an initial plateau and a subsequent decrease corresponding to the shear-induced breakdown are observed in storage modulus curve. And this dashed line actually means the critical strain of these 2 pastes. So we set up the parameters for the time sweep. We selected 0.005% as the strain and 1 Hz as the frequency for the time sweep test. Okay, here, as you can see, these graphs presents the structure buildup of different AAC pastes. Basically, when you increase the temperature of the current condition, the storage modulus increase very faster due to the increasing temperature. it is very, very worth to note that for the MS 1.2 mixtures at the 20 degrees, we can observe a long induction without any increase in storage modulus. But when the temperature increased to 30 degrees or 40 degrees, you can see a rapid increase in storage modulus at a very early age. This means that the temperature indeed has a very significantly influence on the structure buildup of AAC. This similar also can be seen for other mixtures with different activator solutions. The most important things we want to discuss is the loss factor. Indeed, in the AAC paste suspension, there exists a different force. The most important part is the interparticle interaction force and the ballooning forces. Due to the increasing temperature of curing condition, the movement of the particle was accelerated, and the interparticle interaction also was enhanced. And at rest, on one side, the colloidal interactions due to the van der Waals attractive force lead to formation of flocculated structures. On the other side, CSH links and the bridges between the slag fly ash particles are enhanced with progress of the reaction. So as a result, the rigidity and stiffness of AAC paste suspensions are consolidated, showing a gradual increase of in the storage modulus and a reduction in loss factors. With the elapse of resting time, the loss factors reach to a steady value, reflecting the transition from viscous behavior to elastic behavior, or we call elastic state, or we call here it's an elastic state. It can be observed that with an increase in temperature, the time need to reach the elastic state is shorter. As you can, for example, as you can see here, when we increase the temperature from 20 degrees to 40 degrees, the time needed to reach the elastic state was shorter from 80 millings to 20 millings. That's meaning the temperature can increase can lead to more flocculated structure formation in the suspension. To gain further insights into the alkali-activated slag flash mixer reaction process under different elevated temperature, the Arrhenius equation was suggested to determine the apparent activation energy. After calculation, before the calculation, we have to explain how we choose the parameters for this equation. So A is a pre-exponential constant. EA is the activation energy per mole of the reaction. R is the universal gas constant, and the capital T is absolute temperature. The small t is the time needed to reach the elastic state of the paste. So generally, we choose when the loss factor is smaller than 0.087, we think that paste was reaching to the elastic state. So here you can see around 20 millings is the paste. Is when the paste reaching to the elastic state. So yeah, that's the way we choose the parameters for this equation. And as you can see here, after calculation, we obtain the apparent activation energy. The MS 1.2 has the highest apparent activation energy. So which means the MS 1.2 activator solution has the highest reactivity compared to other mixers. And sodium carbonate has the lowest reactivity compared to other mixtures. So besides, we also want to compare the influence of the activators type on the structure buildup and the heat flow at 20 degrees. As you can see the left-hand side graph, this graph presents the storage modulus of 5 different activator solutions. At 20 degrees, at the same equivalent sodium oxide content of 5%, significantly higher initial structuration is observed with sodium hydroxide activator. Then it is followed by sodium carbonate, sodium sulfate, and sodium silicate with MS 1.2 respectively. Furthermore, the structuration rate of sodium hydroxide activator alkali-activated the slag flash paste is higher than the sodium carbonate and the sodium sulfate activated pastes. However, the structuration rate for sodium silicate activator is the lowest, up to around 50 millings. After that time, an abrupt structuration rate for sodium silicate activated paste is observed, which is the fastest fastest among these 5 activators, it is confirmed that the structure buildup of the paste can be controlled by the binary use of the activators. And the right-hand side is the heat flow of these 5 different activator solution. For the peak of the heat evolution, we can see MS0 mixtures shows the earliest acceleration period compared to other mixtures. And for the sodium sulfate, there is no acceleration period for these mixtures. That's also confirmed by previous studies. So we can say like that. Here is the conclusion we made before. The temperature can significantly increase the structure buildup of alkali-activated slag flash paste, and the solution of the combination of sodium hydroxide and sodium silicate with MS ratio of 1.2 show the highest apparent activation energy. And the second point is related to we can use the binary use of the activators to control the structure buildup of alkali-activated slag flash mixtures. Okay, that's all. Thanks for your attention. Any questions?